If you sent a signal through the center of the Earth, pole to pole, it would arrive faster than the same signal sent along the equator. That's not supposed to happen. And somewhere in the middle of that mystery is the reason compasses and GPS systems have been drifting off course. That tiny time difference isn't a coincidence or a measurement error. Scientists have checked it again and again using real earthquakes, and it always comes out the same way. Something at the very center of the planet has been quietly reshaping itself for a very long time, and it's already a bigger part of your life than you'd expect. To understand why, we have to go somewhere nobody has ever actually seen. 6,000 kilometers straight down, at the very center of the planet, there's a solid ball of iron roughly the size of Pluto. Scientists call it the inner core. Nobody has ever seen it, and nobody ever will. The deepest hole ever drilled barely scratches the surface, a few kilometers down out of 6,000. And here's something else strange about it. Earth itself is 4.5 billion years old, but this solid ball at the center might only be 500 million to 1.5 billion years old. Most of Earth's history happened before the inner core even existed. So how does anyone know what's happening down there? Every earthquake sends out waves of energy. Some of that energy travels along the surface, but some of it travels straight down, through the core itself. Scientists pick that up using seismic stations planted all over the world, and by comparing when those waves arrive, they can work out how fast that wave moved through the core. If that core is just solid metal all the way through, uniform in every direction, a wave traveling through it should take the exact same amount of time no matter which way it goes. That's exactly what scientists expected to find, but it's not what they found. Turns out, waves traveling pole to pole move faster than waves traveling around the equator, a small but real difference. That's because something inside that iron ball isn't scattered randomly. It's organized. Picture a balloon, packed full of tiny cotton swabs, all facing random directions. Push your finger against that balloon from any angle, and it takes roughly the same amount of force no matter where you push, because every angle runs into about the same random mix of directions. Now imagine that same balloon, but every cotton swab inside lined up pointing the exact same way. Push along the direction they're lined up, and your finger slides through with barely any resistance. Push straight across the bundle instead, and every single one is standing in your way at once, so it takes a lot more force to get through. Same balloon, same cotton swabs. But now direction matters enormously, because there's no randomness left to cancel anything out. That's what's happening inside Earth's core. Billions of individual iron crystals, packed together under pressure so extreme it's hard to picture, aren't scattered randomly. They're lined up, mostly pointing toward Earth's poles. So the core isn't just solid iron, it's organized iron. But what could possibly line up billions of individual crystals deep inside a planet, all pointing the same direction? The answer comes down to how the core actually formed. It didn't start out solid. It used to be entirely liquid iron. As the planet slowly loses heat, that liquid iron gets cold enough to freeze solid, the same way water freezes in your freezer. Freezing doesn't only happen right at the surface of that solid ball either. Tiny flakes of iron can form higher up in the liquid layer above it, then slowly sink down like snow, landing on the core and adding to it that way too. And when something freezes in a steady, consistent direction, the crystals that form tend to line up with that direction, instead of forming randomly. Here's the clue that confirms it. That alignment isn't the same everywhere. Scientists mapping it across the whole core found it's much stronger on the Indonesia side and weaker on the Brazil side, which means the freezing itself isn't happening at the same pace everywhere either. It's faster and more directional on one side. So why would one side freeze faster? Heat doesn't escape the core evenly. Old slabs of ocean floor sank down millions of years ago and settled directly above the core, beneath Asia. And they're still pulling heat out of that spot faster than anywhere else, even now. This is the leading explanation, though it's not fully settled. A few scientists think something else might be going on entirely, but it's what the evidence points to. Either way, one thing is now hard to argue with. The core isn't just organized, it's actively changing unevenly right now. That doesn't mean it's turning into some lumpy, uneven shape, though. Solid iron, under that much pressure and heat, can still slowly flow. The same way glacier ice is solid, but creeps downhill over years under its own weight. So the extra iron piling up on the faster freezing Indonesia side doesn't just sit there. It slowly flows sideways, across thousands of kilometers toward the slower Brazil side, keeping the whole ball round, even while one side keeps freezing faster than the other. And if something that deep is shifting unevenly like that, what does that actually do to the rest of the planet around it? That unevenness doesn't stay locked inside the core. It reaches all the way out to something you actually use. Here's how. Earth's magnetic field isn't some separate, mysterious force. It's made by the liquid metal layer sitting just above the solid core, constantly swirling, stirred by the planet's spin. Moving metal that conducts electricity generates electric currents, and moving electric currents generate their own magnetic field. That's genuinely it. That process has been running continuously for billions of years, and it's the entire reason Earth has a magnetic field at all. That field is also the exact thing every compass depends on, including the one built into your phone, to figure out which way is north. Now bring back the uneven growth. As the core freezes faster on the Indonesia side, it releases extra heat right into that swirling liquid layer above it, but only on that one side. Due to this, it's not stirring evenly anymore, and that disruption reaches the magnetic field itself. Drifting, weakening in some places, behaving unpredictably in others. This isn't a small, abstract effect. Phones, ships, and aircraft rely on detailed maps made accurately by scientists, using Earth's magnetic field itself. Normally, those maps only need updating once every 5 years, because the field usually drifts slowly and predictably. But that field doesn't always stay predictable. In 2019, the pole was drifting so much faster than expected that scientists had to rush out an emergency fix in the middle of that 5-year cycle just to keep the map accurate. There's also a whole region, stretching between South America and Southern Africa, where the field has grown noticeably weaker. Satellites like the International Space Station and the Hubble Space Telescope orbit the Earth constantly. And every time their orbit carries them through that weak patch, more radiation than normal leaks through, enough that they power down sensitive electronics beforehand so that radiation doesn't scramble their onboard computers. All of that traces back to the same place, a ball of iron 6,000 kilometers down that nobody has ever seen, quietly growing lopsided, one side faster than the other, and reaching all the way up to the compass in your pocket. That's the pattern worth remembering. Somewhere out there, right now, there's another single, hidden trigger quietly reshaping an entire world, a star, a planet, an ocean, a species. And most people will never even know it happened. If you want to keep finding those triggers, subscribe, because that's exactly what this channel digs up.